Hello, everyone, and welcome to the Dean's Lecture Series. My name is Peter Log. I'm the Dean of Science, and it is my pleasure and privilege to introduce today's speaker, Michael Whiticar, a professor in the School of Earth and Ocean Sciences. Before I start, I want to acknowledge with respect the Lekwungen peoples on whose traditional territory the University of Victoria stands, and the Songhees, Esquimalt, and Wasanich peoples whose historical relationship with the land continue to this day. So today's talk by Dr. Whiticar focuses on global methane, environmental and economic considerations. Dr. Whiticar's current research related to the greenhouse gas map, GHGMap, focuses on remote sensing of climate relevant gases, that is methane and carbon dioxide, on land and waters, using microsensors, optical microsensors, on autonomous underwater and unmanned aerial vehicles. Basically robot submarines and drones. It's pretty cool stuff. I do want to say a few words about Dr. Whiticar himself. He is a professor emeritus in the School of Earth and Ocean Sciences at the University of Victoria. He's also an organic geochemist and has specialized in stable light isotopes and natural gases. A few biographical details. Dr. Whiticar obtained his BSc in geology from the University of British Columbia in 1974 and a PhD in marine geochemistry at the University of Kiel in Germany in 1978. He then worked for 2 years as a research geochemist with Petro-Canada in Calgary, followed by 8 years at the German Federal Institute for Geosciences and Natural Resources, and then as the Nordic professor in petroleum geology at the University of Copenhagen in Denmark. So he came to UVic and is a founding member of SEOS, the School of Earth and Ocean Sciences. That is, he has been there from the beginning, 1990. He has since accumulated 120 scientific publications and countless awards. I'm just listing a few here. He's a distinguished fellow of the Geological Association of Canada. He's a Hutchison medalist of the same society. He is also a fellow of the Canadian Institute for Chemistry and a fellow for the Institute of Advanced Study in Germany. And I just checked their website because this is really interesting. I'm German, right? So I wanted to learn more about this. There are not that many international fellows in this society, and Dr. Whiticar is one of very few. So with that, I'll hand it over to him, and I'm looking forward to his talk. Thank you very much.
So you've probably heard a lot about methane over the last few years as a potential greenhouse gas for global warming and global climate change. About 10 years ago, there was a paper brought out, 2012, I think it was, where people were looking at the release of methane from the Russian permafrost. And they did an economic calculation and found out that this had a price tag of about $60 trillion. Whether or not this is true or not, I think still needs to be verified, but it really brings home the point that methane is an important species in the atmosphere and something that we really need to be worried about. So that's what I'll be presenting today, some of my experience and some of my thoughts on methane. To head off the talk, essentially I'll be going through these different topics. Essentially the terminology, what we use is our verbiage. Then I'll talk a little bit about methane burdens, that's the amount of methane in the atmosphere, and temporal changes, so how it's changing with time. Deal with the bigger sources of methane, and then we'll switch into things like energy, how methane is used as an energy source, and currency. We'll talk about methane fluxes, so that means the transport of methane from one box to another. Talk about methane in ice, in gas seepages, in permafrost, gas hydrates, so methane hydrates. And then we'll finish off talking about, again, how methane fits within the climate system. Well, what is methane? Well, methane is a very simple molecule. It's 1 carbon, 4 hydrogen. It is, however, the most abundant organic compound on Earth. It's also present elsewhere in the solar system, including on Saturn and with Titan. There are even lakes of liquid methane on Titan, which is very interesting. But it's a very simple structure that we use. Now, looking at methane, it's often hard to deal with units. So if I said to you teragrams of carbon per meter squared per day or something like that, it doesn't really give you any feeling of the size of this. So I've tried for this presentation to develop a whole new unit. And we could have just taken liters, and you can see here's what a cubic meter looks like if we put all these liters together. But I've decided to introduce what I call the supertanker unit. And a supertanker is essentially 150 million cubic meters of gas. And so this puts a little bit in perspective. If you can see a supertanker on the ocean, then you get a feeling for how much gas is there. But it's quite a bit. Well, we know that methane has been changing in the atmosphere. And if we look at this graph, we can see from the years 2003 to 2005, compared with the later 2008 to 2010, using this heat map based on satellite measurements, we can see that over that period of time, the amount of methane going into the atmosphere, which increases its concentration or burden, its mixing ratio, has increased, dramatically increased. And in particular, we can ascribe where these increases have been most notable. And you can see it's typically within the Northern Hemisphere. So this is something that's very important for us to recognize and to try to understand what is the reason for this increase in methane in the atmosphere. We can look at this in a more of a graphical form, where we look at the time here, the year, and the amount of methane that is being released on an annual basis. In fact, this is much more tightly constrained on a monthly basis. And we can see from the early 80s, the mid 80s, up until about year 2000, that there was this very continual rise in methane. And then there was a short period of time between 2000 and 2007 where there was somewhat of a hiatus. Now, we're not exactly sure what caused that hiatus, but there are several theories. I won't go into those today, because what is important is that since 2007, we've seen this resurgence in methane emissions to the atmosphere, very much on the same trajectory as it was before this hiatus. Today, we're sitting at around 1872 parts per billion. So it has risen then from, just in the time that I've been working on methane, from about 1600 to 1872. So this is a dramatic increase in the amount of methane. And as we'll see again later, it's actually much larger if we compare it to the pre-industrial Holocene periods. Now, this part of the graph just merely shows what the relative change is on a year-to-year type of basis. And we can see that there was almost no change, that we can use this side of the axis to see. There was almost no change in that hiatus period, but now we've continually found that methane is increasing with time. Now, we always like to talk about CO2, much more so than methane. And what we can see is that, in fact, they do tend to track each other. In particular, since that hiatus, we see that they are both rising at approximately the same degree, not the same rate, because of course methane and CO2 are different concentrations in the atmosphere. We have about 407 parts per million of CO2 in the atmosphere, and methane, as I was saying, is about 1872. So there's a lot less methane in the atmosphere than CO2, but as I'll show later on, just because you're small doesn't mean you're not important. Okay, so essentially what we're seeing then is the influence of anthropogenic activities on increasing both methane and CO2 into the atmosphere. So we can actually see this in a more of a spatial sense by looking at a map, a world mapper view of this, where the size of any individual country shown on this map, this distorted map, is proportional to the emission level for that particular country. It's a little bit of a bloated view of the world, but you can see certainly things like United States and Brazil, India, China, and parts of Europe have disproportionately large amounts of methane emissions compared to countries such as Africa or the African continent and Australia and so on. So it begs the question, well, what are these methane sources? Where does this methane actually come that's going into the atmosphere? So that's what we'll deal with next. Well, some of these sources are very easily seen. They're overt emission sources, such as the black smokers that we find at around 2.5 kilometers depth in the ocean, or you can see these as surface emissions through things like volcanic emissions. So these are obvious sources of methane. Now, not all of this vapor going into the atmosphere is methane. Most of it is water and CO2, but there are traces of methane. Here we have sometimes also quite a bit of methane coming out. Well, some of the sources, though, on the other hand, are really hard to detect. They're quiet, but they're not insignificant. Things like swamps and bogs and marshes, where microbial activity produces methane that sometimes you can see bubbling up at a particular water source. But just to put this into perspective, the amount of emissions from wetlands is almost 2,000 supertankers per year. So it's not insignificant, obviously, and makes up about 30% of our total emissions to the atmosphere. So they may be quiet and they may be nice, but they're certainly producing a lot of methane that we need to account for. Well, and some sources are, well, I just say sort of cute, right? Now, cows do actually produce a lot of methane. We would tend to think that most of it is back end, but it's usually front end emissions that we're talking about. And we're producing somewhere in the order of about 600, 620 supertanker units per year from about 1 billion, maybe a few more, about 1.2, 1.4 billion perhaps. But each cow is producing about 60 to 80, 100 kilograms of methane per cow per year. And the reason that it varies is it depends on the feed and the amount of nutrition that the cows get, and hence what their emission rates are. Of course, you're probably wondering, what about us people? Well, we produce about 1 liter of methane per day compared to, say, the 200 to 500 liters per cow. So we're not beholden to cows with regards to methane. Just as a bit of a sideline, if we were able to somehow mechanically capture all the methane that is coming from cows, and most of it is through eructations, in other words, burping, as opposed to flatulation, which we all presume it would be, it does add up. And if we take one of the first Zeppelins, the Graf Zeppelin, which had a displacement of about 2/3 of a supertanker unit, we could fill that, had we all the tubing in place and so on to capture that methane from cows, we could fill that airship in about 35 seconds. So it gives you sort of an idea of the magnitude of gas that bovines, and in particular ruminants, are generating. Well, there are also sources of methane that are coming from our activities that are releasing methane from the subsurface and recovered for our energy needs. And this is a shot of well pads in a drilling district in Wyoming, which is being used for collecting natural gas from hydraulic fracturing operations. So let's move on and talk a little bit about this energy, methane and energy, and what the potential is for that, and some of the questions behind that. One of the first things that we could recognize is that if we compare on an annual basis, looking through time, and look at the amount of energy that is being released, in this case it's in exajoules, that's the standard unit that is being used. We'll come to supertankers again, but if we look at over time, the first thing that becomes immediately obvious is that the total amount of energy that is being used on the planet tracks very closely to the population. Now, we used to think, and it may still be true, but we used to think that because we had a higher population, that there was a higher energy demand, and that's why they would track. But it was more recent, sort of insightful information showing us that perhaps our population is increasing because we have a better access to energy. So it may actually be the other way around. In any case, what we're talking about today is the natural gas component, and in comparison to, say, coal or biofuels, nuclear, and so on. So we do see an expansion in oil at this stage and also in coal, but if we notice the graph only goes out to about 2011, if we took this a little bit further along, we'd start to see the drop in amount of oil production and coal production, and natural gas would be increasing. So where is this gas on Earth, that in the subsurface? When we have a term which we call proven reserves. Now, proven reserves means the amount of gas in the subsurface that can be economically recovered, that we know it's there, but we can also get it out of the ground in an economic sense. This is different from what we call the resource, so gas resource. And you have to be careful when you're talking about numbers, because some publications mix up reserves and resources. So if we look at reserves, means we have about 1.3 million supertanker units as proven that we could take out of the ground economically. And you can see where the primary sources are: Iran, Russia, United States. And you'd be surprised that Canada isn't on the top of the list there. We're actually fairly low with regards to our proven reserves, even though we have a lot going on in Alberta, Saskatchewan, and British Columbia. If we again look at a map of where the actual production is coming from, not just where the reserves are, but where the actual activities are, we can see the top 5 here. I've shown United States, Russia, Iran, Canada, and China. Together, the global production is somewhere in the order of about 4 trillion cubic meters per year, which is equivalent again to about 26,600 supertanker units of production per year. Now, obviously, most of the gas is not being transported by supertankers, it's coming through pipelines and so on. Now, if we look at the consumption, it's almost identical to the production. We don't store a lot of gas. We do in some underground storage systems, but generally what we produce is what we consume. And again, it's about 4 trillion cubic meters per year, and again, about 26,600 supertanker units. The countries are pretty much the same as they were in the previous slide, which showed the production. The order has just changed a little bit slightly in that. Okay. So if we want to look at the annual production and consumption according to region, we can look at this particular demonstration or view of that, looking at the year of production, again, year of consumption. And we can see that, in fact, many countries are increasing in their use. Overall, we're now up to somewhere around the 4,000 billion cubic meters, or the 4 trillion cubic meters, which is again the 26,000 supertanker units. But some countries have not really increased their production, or groups of countries have not increased their production. Others have, though. And I think this is important based on what the actual availability of the resource is and what we're transitioning to as we move from, say, oil to a gas source for energy. So we can break down the actual production as a comparison between more of China, Canada, and the United States. And we can see that there are different sources of natural gas that are being recovered from the subsurface. Now, the conventional one that we're used to comes mostly with oil, would be these natural gases that we're familiar with. However, that is becoming a much less important source of natural gas on the planet. And we're shifting to things like shale gas and tight gas. Shale gas and tight gas are unconventional gases. They're the ones that probably are the most notorious, particularly the shale gas. The difference is shale gas is gas which is in a very low permeable system in a shale, obviously, whereas tight gas is the same thing, very low permeable sources, but typically they would be something like a limestone or a sandstone. So they're both unconventional, but they're also increasing dramatically in their recovery. Shale gas is the one that we know mostly because of things like hydraulic fracturing, or fracking, as we often call it. Coal bed methane is becoming less important as a source. It is recovered by essentially depressurizing coal beds, allowing the gas to evolve from the coal seam, which is then recovered and then essentially cleaned up and sold through pipelines. But shale gas and tight gas is essentially taking over the resource for that. And it doesn't matter which country you're in, we're still seeing that sort of take place. Now, let's just look at what we use this gas for. Well, if we take the example of global electricity, again, using this world mapper, you can see which countries, such as Japan, North America, and the Middle East, and some parts of Europe, are really having dramatic amounts of their electrical supply produced by the burning of fossil fuel, in other words, burning of gas. Other countries and continents, such as South America and so on, Australia, rely on other sources for their global electricity rather than burning carbon-based fuels. Looking a little bit closer to home, and if we want to compare according to province, we also see quite a bit of difference across Canada. Now, in the west, where most of the gas is produced in Alberta, British Columbia, Saskatchewan, a little bit of Manitoba, we see really a dominant use of energy, particularly for electrical and heating, by fossil fuel, in particular natural gas. On the East Coast, it is dominated more by electricity generation, so hydro, and to some case through oil. So there's quite a bit of a difference across Canada with regards to what our energy sources are. Our average household is in somewhere around 88 gigajoules per year, which is essentially 2,300 cubic meters per year per household. Nationally, that means we are essentially consuming about 690 supertanker units per year. And natural gas today represents about 35% of Canada's energy needs. So if we're thinking about changing our energy source, making a change in natural gas usage would be certainly a place to do that. Okay, so let's move on to how methane actually fluxes or is emitted from the geosphere into the atmosphere. And so we can look at these as fluxes, in other words, mass transport into the atmosphere. Now, this is a really busy slide, and luckily, because we're videographing this talk, you can take your time and look at the individual numbers at your leisure. So I won't go through this with painstaking and excruciating detail, but you can see, first of all, that we have sources and sinks, so sinks and sources of methane into the atmosphere. So it's important to understand that it's not just emissions into the atmosphere, but also the withdrawal of methane by the system. And that would either be by photochemical oxidation, which is the predominant sink, but it can also be taken up by the earth, so by soils and in the marine systems and so on. So there's a series of seeps that are, sources that are emitting methane into the atmosphere, and a series of sinks that are withdrawing and drawing down methane from the atmosphere. Overall, the methane burden is about 5,000 teragrams of methane. And that means about 52,000 supertanker units. So that is how much methane we actually have in our atmosphere today. Now, again, we often talk about CO2. In comparison, we have about 8 million supertanker units in the atmosphere. So you'd say, oh, well, methane is just unimportant compared to CO2. And I'll try and persuade you later on in the presentation that that may not be so. If we look at the emission, so not the amount that is in the atmosphere, but how much is going into the atmosphere, so the flux, we can see that methane, which is making up about 18% of the total greenhouse gas contribution, is about 3,800 supertanker units versus about 350,000 supertanker units for CO2. So obviously, the elephant in the room seems to be CO2, but the important thing is not just size, it's your impact that we'll come to. So we can break this down into the various sources of methane that are the big groups of methane that are being introduced into the atmosphere. And that includes things like wetlands, the tropical and boreal wetlands, water bodies, things like gas hydrates that we'll come to, geologic sources, wild animals. And you notice I even mentioned termites. Well, they are a singly very important organism that produces a lot of methane and essentially remineralizes most of the cellulose that we have on the planet. And if we didn't have termites, we would have a lot of leftover wood and so on that has not been decomposed. So they're very important, but they unfortunately produce a lot of methane. Those are what we would term the natural sources. So there's things that really can't do a lot about. They are there, they've always been there. They've changed in their magnitude, but certainly they're very difficult for us to treat as a source. On the other hand, if we look at anthropogenic sources, so human-derived sources, and that includes things like rice paddies, cattle that we saw the cows earlier, landfills, burning of biomass, conventional natural gas and shale gas and coal gas. These are things that we can do something about if we want. And it makes up, in fact, more of the methane emissions to the atmosphere than the natural sources. In fact, about 60% of the emissions today into the atmosphere are coming from us. And we're talking in terms of about 3,000 supertanker units versus about 2,200 supertanker units in comparison. So when we talk about the increase of methane in the atmosphere, it's generally changes in these boxes that are causing that increase in methane. Now, I will point out that there is controversy as to the size of each one of these bars, and I've mentioned that here. But generally, we're starting to get to a fairly good consensus as to the magnitude of individual sources. Okay, so let's look at some of these sources individually. In particular, I'm trying to talk about some of the ones that I think are where we could have a change or could have potentially the most influence. The first thing is, when we say, oh, methane has increased so dramatically on the planet, we should look back a little bit more historically. And how do we do that? Well, one of the easiest ways, maybe not so easy technically, but it sounds easy, is that we look at methane that is contained within the gas bubbles that are included as the snow compresses and compacts and makes ice in places like Greenland and Antarctica. And so we do that. We drill holes and collect samples from ice from Greenland and the Antarctic and from glacial plains and so on. And by drilling down, it's a bit like tree rings on their side where we can actually count the layers, and each layer is an annual layer of snow and thaw. And by extracting the gas from those individual layers, we're able then to establish a time series which tells us something about the amount of methane and CO2, other gases, that have been present in the atmosphere over a longer geologic period, maybe longer anthropogenic period. Here you can see essentially us digging out rather than, this is the Canadian way to do research sometimes, rather than drilling, we just carry a big block of ice home. This is the record I'm talking about, where if we go back in time, here we are present day here, we're going back 800,000 years. So by drilling down in Greenland, in this case, this is an Antarctic core. If we drill down through the ice pack and the ice record, you can look at what the amount of CO2, methane, and the temperature has been as we go back in time. I tend to look at it as a geologist, I tend to look forward in time, right? So this is where we were and this is where we're going to, right? If we started 800,000 years ago. But the immediate thing is that, first of all, the scale. Today for methane, we're at 1872, whereas this record is generally at around 700, maybe 800. So anything that we look at today in the atmosphere certainly eclipses anything we've seen over the recent geologic time, so the last million years or so. Similarly for CO2, we're at 409 parts per million today, and you can see that it's far above anything that we had in the last, say, million years. Now, within that, you can see there is some noise or some jiggle-jaggles going on with regards to methane and CO2 and temperature. So there are changes that do take place, and I won't go into great detail about those changes, but none of them are anywhere looking like the amount of CO2 and methane that we have today in the recent time, and say the last 10,000 years. And we can look at that, blow that up a little bit. And here's the Holocene record, so the last 11,000 years. And we can see the methane essentially been relatively constant until we get to today. In the last, say, 50 years or so, we've gone from 750, 760 up to this 1872. So a dramatic, and this has been referred to as the hockey stick with controversy. And the CO2 does the same thing. So relatively constant over the Holocene period, with the exception of once people started to take over, we've seen this dramatic increase in methane in the atmosphere. So we're able then to use these ice core records as a way to look at what we have done recently compared to what the natural system, where there weren't a lot of people producing methane, has looked like. So let's look at some of these natural sources. We often don't look at offshore natural seepages because we often have a hard time finding them. But we know from onshore seepages that these have been known as very common seeps where people have seen things like eternal flames and so on. So in fact, hydrocarbon exploration in the 70s was based on these seepages. We generally know that where there is a hydrocarbon province, in other words, a hydrocarbon area in the subsurface, we have a surface emanation of gas. And so many of the oil and gas that has been found on the planet, those areas have been also had these surface emanations of natural gas. So for example, here's some shots of this is the Minbu mud volcano in Myanmar. Here we have something in Pakistan, and then Azerbaijan, some of these seeps. We know a lot about these eternal flames, and they've made their way not into just local folklore, but often we talk about these things with regards to religious overtones. Offshore, we recognize them as things we call pockmarks, where we have these blowout craters and so on. And you can see these pockmarks expressed when we do geophysical mapping, but we can also see these when we go down in submersibles, either with or without people. And I'll show you an example of a seep, which is showing the gas emanating up from a gas hydrate area. So my colleagues at the University of Bremen, the Oceanographic Institute, MAREM, has been doing work on seeps for many years, and I've really enjoyed their great videography that they have. And here's an example of methane that is bubbling up from the subsurface from destabilized gas hydrates. So very, very significant sources. The white that you can see in these pictures, in fact, are gas hydrates, and the gas is then essentially destabilizing and bubbling up from there. There are also large sources of methane tied up in permafrost. Now, just like gas hydrates, most of that methane up until now has been relatively stable and has not been being emitted to the atmosphere. However, with the changes in climate, changes in warming of both the oceans and soils, permafrost now is starting to take on a very different view. If we look at the permafrost distribution in Canada, we can see that most of the southern part of Canada, where the highest populations are, we're permafrost free. But as we move up further north, we go from sporadic to discontinuous to permanent permafrost. Now, permafrost is essentially just frozen soil. But within that soil, there's lots of organic matter. And that organic matter, with the microbes, can produce tremendous amounts of methane. And this methane can accumulate and is normally stored and is protected from emission because of that. However, we do know, for example, within the Canadian Arctic, that it will suffer the greatest change in temperature compared to the more central latitudes. So in other words, we're looking at maybe a 3 to 5 degree change in the high Arctic, which we're already starting to see these changes. And as a result, we're changing the permafrost structure. It's starting to thaw out. And as a result of that, we're starting to see emissions of methane from previously stored methane. Some of the work that I've been doing up there includes looking at these things around Fort Simpson and so on, where we see the first signs of this thawing of the permafrost, or the creation of these lakes and these collapsed structures and collapsed scars and wetlands and things like drunken trees and so on. We're starting to see this, and as we have this, these systems are rich in organic matter, and they often go anaerobic, in other words, no oxygen. And as a result, you see the methane bubbling up. So it's not just the methane that is stored within the permafrost, but it's also, you're starting to decay the organic material that is within that permafrost organic matter into methane. And it's a direct path straight to the atmosphere. So the methane that is bubbling out of these systems is going straight into the atmosphere. This can also be seen in what we call these thermokarst lakes, which are, again, these thaw wetlands, these lakes that are produced by the thawing of permafrost. And here's an ice-covered lake where one of my colleagues has decided that they want to demonstrate that there's methane there. I do not recommend you do this at home. But if we look at the amount of methane tied up in the permafrost, it's about 23 million supertanker units. This is a huge potential source of methane. Now, luckily, the current emissions are relatively low, but it has a great potential to change dramatically as we know that the permafrost on Earth is starting to thaw because of global warming. And if you remember, the atmospheric burden is about 52,000 supertanker units. So compare the potential source of this methane tied up in permafrost to going into the atmosphere. And you start to see why we need to be concerned about this dramatically. Now, I've talked about gas hydrates. Gas hydrates are also a huge source of methane, which is currently not going into the atmosphere in great amounts, but has a great potential to be a huge and almost catastrophic release of methane to the atmosphere. Gas hydrate, as you can see here, essentially looks like an ice cube, snow, but it is made up of water and methane, and it can actually be ignited, as I can demonstrate here, especially if you're on the ship and playing hot potato. Okay, so what is a methane hydrate? It's essentially a cage of water molecules, and within this cage, rattling around inside, is a methane molecule. Now, the important thing is that on a volume basis, one volume of gas hydrate would give you 164 volumes of gas for a typical hydrate structure. There's a couple of different structures, but this is the most common one. So gas hydrate is a great sort of storage unit, if you will, for natural gas or methane in natural systems. And where are they distributed? Well, everywhere. We see them mostly offshore because we need to have temperature, a higher pressure and a lower temperature to stabilize the hydrate, so that typically we find these hydrates offshore. We do also find them in the high Arctic regions where it's cold enough, and so we don't need as much pressure to stabilize them. But they're still there, and that's much like the permafrost that I was alluding to. We even have them on the offshore of Canada here. This is just offshore Vancouver Island in Barkley Canyon. And these were actually discovered by Fisher, bringing up fish, and they got these pieces of white ice-looking material in their nets, and were quite surprised that this white material that they had that looked like ice suddenly melted and went away. Essentially what's happening is the hydrate is decomposing at surface temperatures and pressures and is making water and methane. We've also found these in my younger days. You can see that we were looking at these off the Oregon margin, one of the first places that we discovered these gas hydrates. And here we're peeling the potatoes, if you will, to clean off all the sediment from these gas hydrates and using them for all the different measurements that we're trying to do, for example, isotope measurements to determine the source of the gas and so on. We know that this methane that is tied up in this hydrate is predominantly coming from microbial activity, so bacteria that are producing this methane. Well, are hydrates important? Absolutely. If we look at the magnitude of methane, the amount of carbon, if you will, in the methane tied up in hydrates, it's greater than all the other carbon sources that we can think of. If we think about all of the different fossil fuels, if we look at soils and organic matter in land, biota, peat, and so on, add up all the carbon in those sources and compare it against the carbon that's in gas hydrates, and you can see why this has such a huge potential for changing the atmospheric methane. And we're talking about in terms of the maybe 7 to maybe 30 or so million supertanker units. We've had higher estimates. I think we're being a little bit more, as we study it more, we know the occurrence better, but somewhere around, let's say 10 to 25 million supertanker units. Compare that to the conventional reserves of 1.3 supertanker units for gas in the subsurface. And you can start to see the importance of this. Right now, as I say, most of that methane is stable, but we are starting to see changes to that stability as we warm both the land and the oceans. And the big problem we have offshore is that this methane can actually go from the hydrate to the gas state. And as a result, it makes these gas phases underneath the sediment package. This is a sediment package here in the offshore. And it creates what we call a glide plane. And so we can get slumping. We can get big masses, blocks of sediment sliding down the slope, rolling like these are like ball bearings, if you will. The methane is ball bearings. So at that point, it gets released. Essentially, it exposes, doesn't have to go through the sediment package. It can go directly up through the water column. And we've already had examples of that where we can see methane making it to the atmosphere. So it does occur. It's not at this point the large elephant releasing at this point, but we will certainly see some changes with time, and that's one of my concerns. Here's an example of that again. From that Barkley Canyon, you can see this methane bubbling up. So it's a destabilized gas hydrate that is now producing free gas that is coming into the water column. So if you ask me, in my opinion, what's the greatest threat that we have with methane going into the atmosphere, you can see that I'm very concerned about gas hydrates because the magnitude of methane is so large. We only need a small change in the gas hydrate budget to swamp out anything, sorry, the bad choice of term, but to override all the other possible sources that we have. So the question is, are methane hydrates, this giant of methane, is it now starting to wake, and are we ready for that? And where are the examples of this? Well, I was mentioning that the ones in the ocean, because we're having warmer oceans, we could start to see essentially methane come up from these shallow hydrates. This is particularly off the North Slope in Alaska and the Canadian Sounds, up where Mackenzie River enters. We can see that the warming Arctic is causing then a heat pulse into the sediments, which could destabilize these gas hydrates and they come up as gas. But also we have this permafrost, which includes hydrates within them, particularly in the high Arctic. And we know that the high Arctic is warming, and as a result, we're going to start to see, we probably already are, this emissions of methane from these particular sources. And as I showed you one of the early slides, that we do see this resurgence in the amount of methane coming into the atmosphere after that hiatus period. And I'm fairly nervous that this is the source for a lot of that new methane, not just more cattle and so on, but also we're starting to see this destabilization of this big reservoir. And just to show you what I'm talking about, these are people standing up on the crater in the Amur Peninsula in Russia, where we had these huge blowouts of methane. There's so much methane pressure built up that this crater essentially erupted and produced methane, and obviously it would billow up into the atmosphere. A lot of these, this is from the same area, this is where the actual Amur crater is, but there are other examples of it. Now, not all of these here that we can see, if you go on Google Earth, you can see lots of these. Not all of them are these blowout structures. Many of them are just thermokarst lakes, but certainly this is a major point, example of how we can have large emissions of methane dramatically into the atmosphere. So let me bring this discussion a little bit to a close and do my last part here, which is methane and climate change. We know that the climate is warming, the Earth is warming because of the increased radiative forcing that we have by putting in things like CO2 and methane, and that the IPCC has determined that a good safe, whatever safe is, a safe level, it would be about 1.5 degrees Celsius over the pre-industrial Holocene, the PIH. So where are we today? Well, today we're already at 1 degree warming, right? So we've increased our budget to about 1 degree of the 1.5 that we're essentially allowed, that we all talk about. There's actually no particular magic in the choice of this number, but it's a good threshold. So we've only got about half a degree of additional warming that we can tolerate if we are to attain or stay below this 1.5 degrees Celsius. I think it's a good target to aim for. I don't think we want to go above that 1.5. But what it means is we don't have a lot of wiggle room left. We've already spent most of our budget since the 1960s. So we again think a lot about carbon dioxide, and if we look at the atmospheric lifetime of CO2, you can see that it's about a 100-year type of system that we're dealing with. So even if we stop the emissions of CO2 now, they just don't disappear overnight. It lingers for a century. Methane, on the other hand, has a relatively short 12-year, approximately 10 to 12-year lifespan. And if we look at the decay in the amount of methane in the atmosphere, if you put no new methane in the atmosphere, after about 12 years, we would have a halving of the amount of methane that we have. So we can see that it decays very quickly. Well, that's good news. That means if we stopped the anthropogenic emissions of methane into the atmosphere, that would decay out relatively quickly compared to CO2. So making a change in the amount of methane emission would have a bigger impact on the overall budget. But it's more important than that, or more tricky than that. First of all, the radiative forcing, in other words, the amount of greenhouse gas effect that you can have from a molecule of methane is much larger than that for CO2. And so if we just added in a pulse of methane into our atmosphere, let's just play the game that we have no carbon dioxide and no methane in our atmosphere, and we put in what our annual emission is of methane into the atmosphere and watched it and monitored it over time, we'd see this rapid rise in temperature. And then as the methane is essentially oxidized out of the atmosphere, you would see this drop. CO2, on the other hand, it would rise if we put in, of course, we're putting in 10 times the amount, right? So if we rise that up, it would actually then decay much more slowly. So what we put in for CO2 lingers longer. And you'd say, well, that makes it more deleterious. Yes, but on the other hand, we can make a change in methane much more quickly with regards to our radiative budget. But the important thing is, if we start at this T0 and watch the first decade for this pulse of both CO2 and methane, they both result in about the same degree of warming. Even though the amount of CO2 that we're putting in is magnitudes larger, right? We're talking 350 supertanker units versus 3,500 supertanker units, right? We see this very close matching in the amount of radiative heating from the two species. So in other words, if we want to make a change, we get the biggest bang for our buck with methane than we do with CO2. So we are often confronted with this term called global warming potential. And so it really depends on the length of time that you use for this global warming potential to compare. And part of the problem has been that we've often compared methane to CO2 rather than dealing with methane as itself. And because methane has such a shorter lifetime than CO2, we've generally said, okay, if we take CO2 to have a 100-year lifespan, what does methane do in 100 years? And we end up coming up with a global warming potential of about 25 or 28, depending on the calculation, which is actually wrong compared to looking at what it would be if we just use the normal lifetime of methane. If we take the global warming potential period to be 20 years as opposed to 100 years, now the importance of methane again rises, but it overestimates in this particular later stage of its life. So although it's been very convenient to use global warming potential, it is physically not a very good way to do this. And I can express that a little bit more clearly. Again, this is our 1-year pulse here. And if we added these pulses of 5-year, 10-year, 20-year pulses, meaning 20 years addition of methane that we would have normally each year from anthropogenic sources going into the atmosphere, you can see the rise in temperature associated with it. So in the next 20 years, if we don't change anything from our anthropogenic emissions, that's where we're going to be. And we're at 0.4 degrees. Remember, we only had half a degree headroom. So do nothing else, right? we're going to, even if you had no more CO2 put into the atmosphere from anthropogenic sources over the next 20 years, if we stopped it for some miracle, the methane would still do that 0.5 degree. So either one, right, you can see either one in 20 years time, both the CO2 and the methane will give you that approximately that 0.5 degree rise. So we got 20 years, and we don't need to change the CO2 or the methane. We have to change probably both of them in order to attain that 1.5 degree change. So you can see my nervousness because I've shown you that we have big sources of methane that can ultimately be ejected into the atmosphere, which could even push this higher. So although we are very concerned about CO2, and rightly so, I hope you understand that I'm also concerned about methane. So just to bring this back to the finish, remember there are large amounts of methane emitted through natural sources, but there's not a lot we can do about that. There are about 40% of the methane going into the atmosphere, but it's very difficult for us to change those by any sort of remediation. However, the gas hydrates that we've seen here are relatively small today, but have a huge potential to be a big source in the future. And though we can't do anything about it, once it started to thaw, we have to be aware that the climate change that we are doing right now, this heat pulse that we're putting into the system, will ultimately lead into this destabilization that we're already seeing in the high Arctic. On the other hand, we have all of these anthropogenic sources that we could make differences on. For example, rice paddies, they produce their methane generally by making an anaerobic flooding of the paddy itself to start the rice. So if we need less water, it's less anaerobic, we produce less methane. Some strands of rice will grow more easily without producing so much methane. So we can make changes there. We have ways of, say, inoculating cows, and there's some studies using algae that reduce the amount of methane emissions from ruminants. I think that's important. Probably easier than putting tubes in all cows, as we were talking about earlier. Membranes can be put onto landfills and do gas collection systems from that. Biomass burning, again, we should be careful about what we're doing, not just burning forests, which is difficult for us, but also burning standing crops after we've harvested and so on. And then changes in the natural gas process, which we hear a lot about, particularly in Canada with the new regulations of wanting to drop the emissions of methane from oil and gas operations by 50% in the next 20 years or so. We can make changes there, but these are the places where we can make changes, and I think we need to. So just to wrap up, I give you one last slide of what I'm doing, and not, despite all this worry, we're trying to make these measurements. And now we're using a small little drone. Others are using satellites, but on this particular drone, we have a very sensitive methane sensor. And we're able then to fly this over various sources. We were supposed to have gone out this year to the Permafrost. We're unable to because of the C-19 restrictions, but we're hoping then to map out larger districts. With that, we can produce things like emission maps for particular sources and determine quantitatively how much methane is coming out from individual sources. So that's what we're doing, and I thank you very much for your interest.